Hi, everyone. My name is Skylar, and I am an ambassador for the American Association of Variable Star Observers. And today I'll be talking about the observable Barycenter motion of celestial objects, basically things like center of mass and how that relates to topics in astronomy. So let's go. Okay, so bare bones, start with the basics. What is center of mass? Well, I can tell you right now. Let's say I have an object. I've got my little green robot alien stuffed animal. I'll call him Steve. Basically, if I throw Steve in the air, he goes on a parabola. It's easy enough. Basically, if I wanted to know how fast Steve was going or where Steve would land, it would be really annoying if I had to represent Steve as taking up space. If I had to calculate where his ears would land, where his arms would go, how fast they were going, just basically like all of the parts that make up Steve, if I had to calculate all of them separately, that would be a mess. That would be awful. But as it turns out, we can represent objects as basically the center of mass. Objects can be represented mathematically as being a point traveling through space. Basically, the center of mass is the average position of an entire object represented by a point. So I don't have to calculate where all of the different parts of Steve go if I throw him in a parabola. I can just calculate Steve's center of mass as he travels through the air. And the shape of the object doesn't matter either. All that matters is the position of the center of gravity or the center of mass of the object. We can represent it as a point source. That is very convenient. But what happens if the object that we're talking about is actually a system of objects, a system of isolated particles? The same rules apply. I have a diagram here. Basically, let's say you've got like a dust cloud that's like floating through space. It's like got like loads of different dust particles going which way in that. But that whole dust cloud can be represented by the average positions, the average centers of masses of all of those particles into one final average center of mass. Let's say you've got like a dust cloud floating through space. It's going in a single direction. That dust cloud can be represented by a single center of mass of the whole cloud. As long as the system is closed, nothing outside of the system is acting on it, it has just one center of mass. Okay, so now that we have the concepts down, let's talk about some math. Basically, I've kind of qualitatively written it out here, forgive my handwriting, but we can calculate the position of a center of mass of a collection of objects in a closed system. So like, let's say you have one particle here, another particle here, bunch of particles here and there. But the position of the center of mass of your entire dust cloud can be calculated using the mass of the first object multiplied by its position. And when I say position of an object, I mean with respect to some kind of origin. Like let's say I put my origin, I've got this big dust cloud, I put my origin here. And when I say origin, I mean a place where the position could be like 0, 0. Well, the position of that first object is going to be the distance between the origin that I've kind of arbitrarily chosen and that first particle. As long as you choose a consistent origin, this formula will work. Like you use the same origin for all of your particles, basically the distance from that origin to each particle. That is what is known as the position of the first particle. So you have mass of the first object multiplied by the position of the first object, plus the mass of your second object multiplied by the position of the second object, plus the mass of the third, yada, 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 for however many particles you have. This can really go on forever. But all of that has to be divided by the total mass of your entire system, the total mass of each object added together. And that's basically the gist of it. That's how you calculate where your center of mass will be for a system that has many different objects kind of in a closed system. I've also written it out in a more mathy way with variables. Basically, let's say you have like a 2D grid and you pick your origin here. That's going to be your 0, 0 point, your origin. You can basically calculate the x-coordinate of the center of mass using the x-coordinates of each particle. And you can also calculate the y-coordinate of your center of mass using the y-coordinates of each particle. And you can also combine those two equations. It's more of a note-taking thing. This is basically, this bottom part is the same equation as these two, just kind of combined if you're using vectors. Okay, so how does this relate to astronomy in any way, shape, or form? Well, we have something called Barycenter motion, and I'll explain it like this. Let's say you have two objects in space, could be stars, could be planets, could be whatever. Let's say two stars, actually. You have two stars of the same mass. They're going around each other, they're orbiting each other. It's a closed system. You have two stars that are orbiting the same center of mass because they are gravitationally bound to each other. They are orbiting one another. But let's say you increase the mass of one of the stars by a lot. Basically, the first object is going to be much greater than the second object. Well, the orbit of that first object is going to be a lot smaller because it has to drag its weight around everywhere. And meanwhile, that second object is just going to be, flying because the first object is going to be much bigger than, like, maybe much more important than the second object is going to be. This is basically the case for, let's say you have like a star and maybe a smaller planet. Let's say you have like a planet going around it, and it doesn't gravitationally affect the star that much. But let's say you have maybe like a Jupiter-sized planet, or like a big planet, maybe like a smaller star, and it's going to maybe affect the motion of that star a little bit more. And maybe it's observable. Well, that motion is barycenter motion. It's basically when the larger object is noticeably moved because of the smaller object. We kind of have these two scenarios here. Well, this has real life applications in astronomy. This is basically all of orbit physics. It's got many, many different cases that can be applied in different places. For example, let's say you have the case where you got like an asteroid, small body, a rock, basically. And what if it's got a moon? It's got a tiny moon and it's in the Kuiper belt. Varda and Ilmare is such a system. Basically, you have this Kuiper belt object. It's this rock floating through space outside of the orbit of Neptune, and it has a moon that's orbiting it. And we can measure how much Varda moves because of Ilmare's motion around Varda. We can basically measure Varda's movement, and we can basically know that it has a moon because of this motion. And the same physics applies for much bigger objects. You have a small system like Varda and Ilmare, they're basically two rocks, or you can have these big stars that are orbiting each other, like in the system we were talking about before. These are binary star systems, and there are quite a lot of them, actually. If you just looking in the night sky and you see a star, it could actually be two stars orbiting each other. They're just so close and so far, like close to each other and so far away from you that you don't see both of them. And two stars orbit each other around a center of mass, same physics. And finally, like terrestrial object to terrestrial object, star to star, why not start a planet? If you've got like a big star, maybe a pretty big like gas giant planet, maybe that planet will gravitationally pull on that star enough to where it is observably moving, even wobbling a little bit. And this is called the wobble method for exoplanet detection. We have discovered planets that orbit stars like outside the solar system, very far away, because the star is moving because of that exoplanet. We can't observe exoplanets directly, or at least that is very rare when we can. So we always have to use indirect methods because planets don't emit light. So if a star moves because something that we can't see is orbiting it, that is called the wobble detection method. Okay, and one final example, I have a real life example of Pluto and its moon Charon to show you. Basically, the deal with the dwarf planet Pluto, it's got a moon, and it's got like a pretty big moon for its size. Charon is 1/10 the size of Pluto. That doesn't seem like a lot, but it is. Basically, is it enough though to where Pluto would exhibit barycenter motion, where we could see it move and wobble because Charon is orbiting it? Basically, in other words, is the barycenter of Pluto and Charon outside of Pluto? Basically, if something exhibits barycenter motion, the center of mass of the system is going to be outside of the radius of that larger object, basically. And you know what? Let's find out right now. We can calculate this. This is calculatable. Let me go ahead and share my screen, actually. I have some work to do with you guys. Let's see. Screen mirroring. I've written down a few things just to start us off. Bingo. Okay, so this is what we have to start off with. We need a few variables or values first. We need the mass of Pluto, we need the mass of Charon, and we need the distance between the two of them. We have all of these. And also, I have the radius of Pluto here. I'm going to use that after we calculate where the center of mass is. We also have our equation that we're going to use, our center of mass equation. And I also have, if it was a little hard to kind of visualize the grid that I was talking about earlier, here's an example. Basically, we have two particles. We have Pluto, we have Charon, and I've made a grid where the center of Pluto is going to act as our origin, and Charon is a little bit to the right. So we need to calculate where the center of mass of the system is, and we will do that right now. Okay, center of mass. Let's see. We need mass of Pluto multiplied by the position of Pluto. And we're going to give the same treatment to Charon. Let's see. To Charon. There we go. And we're going to divide everything by the total mass of the system. For example, we have the mass of Pluto plus the mass of Charon. This is going to be our equation. And now we can start plugging in numbers. The mass of Pluto, according to JPL website, the website for the Jet Propulsion Laboratory from NASA, is about 1.3 times 10 to the 22 kilograms. That is very heavy. But it's actually, Pluto's still a dwarf planet. If you look at the masses of things like Jupiter, it's like dwarfed in comparison. And we multiply it by the position of Pluto. But if we look back at our graph, we see that we have positioned it in such a way that Pluto is our origin. The center of Pluto is our origin. This point is going to act as 0, 0. So what happens then? What happens when we put one of our particles at the origin? Well, that position is just going to be 0. We can just put in 0 right there, and that'll eventually cancel itself out. So we can keep moving. The mass of Charon is going to be 1.55 times 10 to the 21 kilograms. It's an order of magnitude smaller than Pluto, but we will see whether or not it is, whether or not it's negligible. And our position of Charon is not going to be 0 because the distance between Pluto and Charon, their centers, is 19,640 kilometers. We have that distance, and we can multiply this by that. That is going to be there. We still do need the mass of Pluto, even if it's going to be canceled out in the numerator because we are going to add the total system together. There we go, there we go. We've kind of drawn all of this out. And we can immediately cancel this out, just take it out, it's 0. And make this a little bit easier on ourselves. This is going to be our numerator, and the denominator, again, is going to be the total mass of the system. Add these two things together. And before we calculate our final number, let's check our units. That's a very good habit to get into. Let's see, I'm going to use pink. These two numbers are going to add together. So the final units of the denominator are going to be kilograms. And the units of the numerator are kilograms multiplied by kilometers. That's a little bit nonsensical right now, but these 2 kilograms cancel out and we have kilometers as our final answer for our units. And that makes sense because we are looking for the position of the center of mass of the whole system, and it will be in a unit of distance. Checking your units, make sure you're going in the right direction. It's always a good habit. And our final number is going to be 2,292 kilometers. I'll leave it up to you to plug in those numbers into a calculator, but this is going to be your final answer. And what do we do with this number? Why is this significant at all? Well, we can go back to our graph up here. This whole thing, it's not really going to be to scale, but it's enough to make a point. We have the radius of Pluto. Remember, I had this number stowed away from before. It's going to be, the radius of Pluto is 1,188 kilometers. That is on our graph. It is here, 1188. And well, the position of our center of mass is a greater number than that. The center of mass is going to be between Pluto and Charon, but it's going to be, that was the eraser, it's going to be about here. And that center of mass is outside the radius of Pluto. So basically what's going to happen if I clean this up a little bit to make my point, take out all this. If this is your center of mass, you're going to have Pluto's orbit kind of look like that. Imagine if that was a good circle. And Charon kind of going around the system, that is a worse circle. Okay, kind of like that. So you have this kind of behavior for the system. And that is the magic of center of mass. I have one more thing to show you guys. We can see this in action. We can see the movement of Pluto and Charon. This was taken by NASA's New Horizons probe that recently went past Pluto. And it captured this in action. We can see Pluto kind of moving with a Barycenter motion because of Charon. So yeah, this had been mathematically calculated, but this is a really good GIF of the Pluto and Charon systems, Barycenter motion. You can kind of see this in action. All right, so that's about it for me this time, and I will be sure to come back with more astronomy topics. Thank you very much for joining me.